Hi everyone, welcome to the fifth lecture of the series on control of mechanical systems. In this lecture, we discuss the control of simple pendulum. Here is the overview. We start with the mathematical modeling of simple pendulum. Then we move on to the control of simple pendulum, in which we discuss the sliding mode control and model predictive control approaches. Here we consider the time domain modeling of the simple pendulum as shown in figure 1, in which m is the mass of the pendulum, l is the length, theta is the angle made by the pendulum with the vertical axis, T is the torque applied to the pendulum. Then, by applying the torque balance equations, we obtain the dynamics of the simple pendulum as in equation number 1, in which J is the moment of inertia, and for the simple pendulum, we have J is equal to ml square. B is the friction coefficient, and G is the acceleration due to gravity. Here, we have a term with sine of theta, which makes the dynamics of simple pendulum nonlinear. Therefore, the simple pendulum can be represented by a second order nonlinear differential equation. Now, by substituting J is equal to ml square and the control input U is equal to T, the state variable x1 equal to theta and x2 is equal to theta dot, we can rewrite the second order differential equation as two first order differential equations. And by combining x1 and x2 into a single vector, we can represent this equation as in equation number 3, which is in the form of x dot equal to f of x comma u and y is equal to g of x, which is the form of a standard nonlinear system. Next, we move on to the control of simple pendulum. We start with the sliding mode control or SMC approach, in which we use the state equation of the simple pendulum as in equation number 4, and the sliding variable is chosen as a function of the output error. So S is equal to YR minus Y, where YR is the output reference and Y is the actual output. Then we define the slide mode control law using the twisting controller, for which the control law is as in equation number 6, where U is equal to minus R1 times signum of S minus R2 times signum of S dot. So here R1 and R2 are the switching gates. For more details on SMC and twisting controller, the lecture series on SMC can be referred, for which the link is given in the description. The simulation parameters are chosen as in equation number 7, in which we select YR is equal to 2 plus sine of t, and the switching gates R1 and R2 are chosen as 15 and 5 respectively. For the simple pendulum with the sliding mode control, we obtain the response as shown in this figure. Here, this first plot shows the response of x1 with the time, in which the black one is the reference output and the red one is the actual output. Here we can see that the output is tracking the reference. And this figure shows the plot of the sliding variable with the time. So we can see that the sliding variable is converging to 0, which basically means that the output is reaching the reference. This shows the plot of the estimation of S dot. And here we have the plot of control signal. This figure shows the plot of the sliding trajectory, in which we plot S versus S dot, which is basically the output error versus the output error dot. So here we can see that it starts from some non-zero values and eventually it converges to the origin. It basically means that the error is converging to origin. Next, we move on to the model predictive control or MPC approach, for which we use the discrete time model of the simple pendulum. We have the continuous time model of the simple pendulum can be represented as in equation number 8, which gives x dot equal to f of x comma u, where f is this function. From this equation, we can obtain the discrete time state equation of the simple pendulum as in equation number 9, in which we use a sampling period t and we discretize this equation. Here, for a small value of the sampling period t, we can approximate this x dot as xk plus 1 minus xk by t. Then taking this t to the right hand side, we get xk plus 1 minus xk equal to t into f of xk comma uk. This results in xk plus 1 equal to xk plus t into f of xk comma uk, which gives this discrete time state equation. Note that here this f and this f are two different functions. So we should represent this by some fc and this by some fd. And we have fd is in the form of xk plus t into fc of xk comma uk. In MPC, we use the discrete time state equation for predicting the state trajectory over a finite prediction horizon, and the control input sequence is computed for optimizing the predicted behavior. Here, we are not going into the details of MPC, And for more details on MPC, the lecture series on MPC can be referred, for which the link is given in the description. Now, the system parameters are chosen as in equation number 10, and the simulation parameters are chosen as in equation number 11. And for MPC, we select the constraint set parameters as in equation number 12. In the simulation, we consider two types of problem. The first one is the stabilization problem, in which the state reference XR will be 0. And the second one is the set point tracking problem, in which the reference XR will be non-zero. Figure 4 shows the response of the simple pendulum for stabilization, in which the state reference will be 0, and our objective is to drive the simple pendulum from non-zero initial state to 0. And we can see that with MPC, we can able to stabilize the simple pendulum. And the control input for MPC is given in figure, and it shows that the control input satisfies the constraints. Next, we consider the simulation of the simple pendulum for set point tracking, in which we consider a non-zero reference XR. Then our objective is to drive the system from some initial state to XR and maintain the system at XR. In steady state, we require the states of the system should be stay at XR. Therefore, in steady state, we require xk equal to xk plus 1, which should be equal to XR. And this gives the steady state equation XR equal to f of XR comma UR, where UR is the steady state control input. The system parameters are chosen as in equation number 15, and the simulation parameters are chosen as in equation number 16. And here by substituting the steady state condition, we get UR is equal to 4.69. And the constraint set parameters are chosen as in equation number 70. Here, the control constraints should be chosen in such a way that this UR will satisfy the control constraints. Then we have the response of the simple pendulum with MPC for set point tracking, which shows that the states are starting from some initial states and is moving towards the reference values. And this plot shows the control input. And here we can see that the control input satisfies the control constraints. And in steady state, the control input converges to the value of UR. The MATLAB course for the simulation can be downloaded from the link given in the description. That completes this lecture. Thanks for listening.